Hello guys, welcome to another lectures with Urban Planning Studio Hub. In these lectures, I would like to explain to us a topic on normalized difference ratio for spatial indices using satellite imagery from Landsat 7 and Landsat 8 respectively. Now, Landsat 7 and Landsat 8 data have been widely used for image classification. This classification includes models like the Normalized Difference Vegetation Index, Normalized Difference Building Index, Normalized Difference Water Index, and this analysis from these models has been widely used in the field of spatial analysis globally. Now, the process of extracting these satellite images, first of all, by visualizing data from online sources like Landsat data, Sentinel data, spot imagery, amongst others. So for these classes, we'll be focusing on Landsat data. Now, the normalized difference ratio indices can be created on ArcGIS, GIS Pro, QGIS, and other GIS software programs. Now, this is used to create land use or land cover classification imagery. Now, this model uses a technique. It categorizes pixelated image format, that is satellite imagery that covers the spatial data of a particular region or area of interest, and it uses the pixel to make classifications for the physical attributes, that is the physical, both the natural and anthropogenic features of the Earth's surface. Now, Landsat 7 has a total of 8 bands, while Landsat 8 has a total of 11 bands. Now, for analyzing vegetation, buildup index, water index, we basically use 4 bands, which are the green, red, near infrared, and short wave infrared. Now, on the next slide, here is a table housing Landsat 8 and 7. Landsat 7 is the enhanced thematic mapper, which you can see that it has the bands from number 1 to 8 here, while that of the Landsat 8 has 11 bands from 1 to 11. Now, the TIRS stands for thermal infrared sensor, NIR near infrared, and then short wave length infrared. Now, in order for us to understand how the satellite works when it comes to image capturing, there is what we call the Spectra reflectance curve. This is where we have the relationship between electromagnetic spectrum and the associated percentage reflectance of given materials. It means that the features on the Earth's surface can either be that which have the wavelength which radiates or reflects. It either radiates or absorbs. So this wavelength here, spectral wavelength, is trying to show us the surface, that's the reflectance here, which is in the vertical section, and then the wavelength, which is the horizontal section in the spectrum. Now, for water index, it ranges from and the wavelength is right in micrometer. So the water does not exceed 0.8. That is its senses. If we can go back, you can see the range for the wavelength in micrometers, so you can see that. So this is what enables us in order to understand which of the wavelength will fall into the category for water, the vegetation, the soil, and a lot more. You can see here we have the visible light, here is the near infrared, and then the intermediate infrared. Okay, so we'll be coming to that. Now, the first one we'll be taking is the Normalized Difference Vegetation Index. This is commonly used for vegetation observation globally. Now, we have other methods of actually classifying vegetation cover. That is the Enhanced Vegetation Index, EVI. We have the Perpendicular Vegetation Index, PVI. We have the Ration Vegetation Index, RVI. Now, in general, healthy vegetation are good absorbers of electromagnetic spectrum in visible light. Okay, and the chlorophyll present in the green are good absorbers of the blue wavelength, which ranges from 0.4 to 0.5 microwave, and then also the red wavelength, which is 0.6 and 0.7 microwave, and then it also reflects green, 0.5 to 0.6 in the spectrum. So but our eyes in normal sense perceives the green. It perceives it is actually blue, a light, but we perceive it as green. So the healthy plants have high reflectance of the near infrared, that is between wavelength 0.7 and 1.3 micrometer. Now this is primarily due to the internal structure of the plant. Now high reflectance in NIR and high absorption in red spectrum. Now these are now the two bands, or rather we call it the two wavelengths we use in calculating the vegetation index. One is the near infrared, and then that of the red spectrum that absorbs. Okay, now the formula for calculating the normalized difference vegetation is taking the difference of the near infrared from the red spectrum to the ratio of the near the sum of the near infrared as red and then the red spectrum. You can see the formula here. In short form, it is NIR minus red all over NIR plus earth, and then that for band 7 on the Landsat data, we use band 4 and band 3 to calculate the difference, the vegetation index, and that of Landsat 8 we use band 5 and band 4. Okay, now in the index there's an explanation. The NDVI value varies from -1 to 1. Now the higher value of NDVI reflects near infrared, means dense greenery. So in general the breakdown for the index is that if your value falls between -1 to 0, it represents water body. From -0.1 to 0.1, it represents barren, sand or snow, or we call it bare land. From 0.2 to 0.4 represent the shrubs and the grassland, and then anything from 0.6 to 1.0 represent dense vegetation or tropical vegetation. Okay, now we actually use on the software, most especially ArcGIS or GIS Pro, we use what we call the Raster calculator in order to compute the normalized difference vegetation index. I'll be using a case study to practicalize both the normalized for the vegetation, for the built-up, and then for the water body. Now this is an example of a classified NDVI of a city called Kumila City. Now you can see the range from 0.5 to 0.71 is defining the green areas, and then it runs down to other land covers like that. Okay, now the second on my list here is the built-up index. Now the built-up index too also have a lot of analysis. We have a lot of models. We have the normal one we'll be using, that is the normalized difference build-up index. We have the build-up index, we have the urban index, we have the index-based build-up index, we have the enhanced build-up and barrenness index. These are what we use oftenly to calculate the built-up index. Okay, now the built areas and bare soil reflects more of short wavelength than near short wave infrared than near infrared. Now water body doesn't reflect on infrared spectrum. That's why you see when it was here, you can see it stopped at visible light. It didn't really cross through, it didn't make it through the infrared. Okay, so that's why they're specifying it here, that water body doesn't reflect in infrared spectrum. Now in the case of green surface, reflection of near infrared is higher than short wavelength infrared. Okay, now for better result, we use a build-up index. The build-up index is the index for analyzing the urban pattern using the build-up index and the vegetation index. Now the build-up index is the binary image with only high positive values indicating built-up and barren, thus allows BU to map the built-up areas automatically. Now we can calculate the normalized difference building index, but in order to get the actual, or to get a more accurate result, we use what we call the built-up index, that's the BU, where we take the difference. Okay, So we take the difference of the normalized build-up index, rather we take the difference of the normalized difference vegetation index from that of the normalized build-up index in order to get the build-up index properly. Now that's what we use in order to classify the accurate result for the build-up index. So the formula for calculating the NDBI is simply we use the short wave infrared and the near infrared. So we can see that we have the ratio of the difference to that of the sum of the short wave infrared and the near infrared. Now for Landsat 7 data, we use band 5 and band 4. So also for Landsat 8 data, we use band 6 and band 5. You can see that we're talking about the short wavelength and the near infrared, and then band 5 is the near infrared. That's why we use this as the build-up index. Okay, now it also has a range. Now the normalized difference build-up index lies between -1 to +1 in the index 2. The negative value of NDVI represents water, whereas the higher value represents the built-up areas. Now it means the negative value is the water and the positive values also is known as the build-up area. Then this is an example for the normalized build-up index for the same city, Kumila city. Now you can see that where you see the red defines where our built-up areas are, while that as the color graduates, it also gives us a different other land covers. And you can see that this is actually a time lapse from 1998, 2008, and then 2018. You can see the footprint of the build-up area, how it increases with as time moves on within decades. So let's move on to let's proceed to the third. We have the normalized difference water index. Now this index is used for analyzing water bodies. The index uses green and near infrared bands to remotely sense the spatial data. Now the normalized difference water index can enhance water information efficiently in most cases. It is sensitive to build-up lands and result in overestimated water body. Now the NDWI product can be used in conjunction with NDVI change product to assess content of apparent change area. Now the water body have low reflectance. It only reflects within visible portion of electromagnetic spectrum. Now the water body in liquid state are generally high reflectance on blue wavelength in the spectrum from 0.4 to 0.5 micrometer, and in the spectrum than green, which is 0.5 to 0.6, and red as well, and this in the spectrum. Now clear water having greatest reflectance among the waters in the blue portion of the visible spectrum, so water appears blue. Turbid water has higher reflectance in visible spectrum. Now there is no reflection in near infrared and beyond. That's what we explained here. For water, it ends immediately after the visible light in the spectrum, so there is no reflectance here once it reaches the near infrared or the intermediate infrared for the water. Okay, now let's proceed. Now the index uses the near infrared and the short wavelength bands in order to calculate the normalized difference water index. Now for Landsat 8, we use band 4 and band 5, and Landsat 7 we use band 4 and band 5. We take the ratios of the difference to that of the sum, while that of Landsat 8 we use band 5 and band 6 to compute their water index. Okay, now the water index have been modified by Zhu in 2005, where he actually used this. He tried experimenting by using different bands. Excuse me. So he tried band 2 and band 5, and then it became apparent that this gave a more accurate result. So we call this the modified Normalized Difference Water Index, that's the NDWI. So it also have the index, and you can see the index ranges from -1 to 1, and generally water bodies has a value greater than 0.5. So once you have values greater than 0.5, we will define it as a water body. Now vegetation has much smaller values, which distinguishes vegetation from water body easily. Buildup features having positive value and lies between 0 to 0.2 in the electromagnetic spectrum. So you can see these are an example for the same area of study for the water index. Just as the result states here, it will state that the water has a greater value than 0.5. So anything from 0.5 is the water body for us here. So that will be the little introduction about or understanding about normalized difference ratio for spatial indices, what we use to classify using Landsat 7 and Landsat 8 data strictly. And this table here gives us a breakdown of how to understand the types of wavelength we have, their electromagnetic wave in the spectrum in micrometers, and also the resolution of the imagery. So with this, we've been able to understand how it works, more especially with the spectral reflectance curve, where some of the sensors or data are sensed between the visible light. We have the near infrared and the intermediate. And we also learned that the water doesn't cross, it has no reflectance in the near infrared or intermediate infrared. So that is what we use actually to understand satellite imagery data, and that is also what we use excuse me, to enhance our understanding once we are using satellite imagery for our studies. So guys, I would like to terminate the lecture here. I'll meet us on the next one. I'll try to get a case study of a particular area, then I'm going to practicalize the three. That's the Normalized Difference Vegetation Index, Normalized Difference Water Index, and Normalized Difference Builtup Index. So guys, thank you for having you on this one. Catch you on the next one, and peace out.